Salam Rahmatullah. An important application of QP is the solution of support vector machines in machine learning. So the SVMs are used in classification problems in machine learning, and it's one of the most important uh, algorithms used for classification tasks in machine learning, right? So we can formulate the support vector machine, the SVM problem, as a QP problem, and then you can solve it using the convex optimization tools, right? So the central idea in SVMs is to find what is called a hyperplane. Okay, so before that, um, how do you formulate the um, classification problem that you uh, have a set of classes? Let's say you have pictures of cats and dogs, and you need to classify which is which, right? So how do you do that mathematically? You convert the the image into a vector, a point in space, right? So you have multiple points for dogs and multiple points for cat images, right? And you put them in the space. So now you converted this problem into a geometrical problem. Now you need to find a line in 2D, a plane in 3D, or a hyperplane in higher dimensional spaces to separate those lines, those points, sorry, right? So this is the main idea. You have a set of points in space, and you need to find the best hyperplane to separate those two sets of points. Okay, so this is the training procedure. The training procedure is to find the best hyperplane that separates the points, right? In the inference, so when you want to classify, you just see, is this point the new point, which is a new image, is it in the left hand side or the right hand side of the hyperplane? So let's say that on the left hand side you have dogs, and on the right hand side you have cats. So if the new point, you throw it and it falls on the right hand side, so it's a cat image. So this is how the machine classifies those images, right? Okay, so SVM improves on this concept. In addition to having hyperplanes, it has margins. So what is the best way to classify this sets of points? So I think I have an image here, right? So here, right? So here you have class 1, which is the cats, and class 2, which is dogs, right? So the idea is to find the best hyperplane. As you can see, you can have multiple separating hyperplanes here. So which is the best one? So the idea of the SVM is to find a kind of a margin. So it's not here. So a margin is something like that. Let's change the color, right? So we want to find a hyperplane like this, another hyperplane like this, right? And we need to maximize this margin between the two hyperplanes. And the central hyperplane will be the one in the middle. So the one that is used for classification is the one in the middle between the two margins. So this is the idea of the SVM, is to find the maximum margin between the two classes of points. Okay. So we can formulate it in a mathematical terms, right? So we have a set of points, right, in hyperplane, and they satisfy this equation here, 4.66, where W is the normal vector to the hyperplane that we want to find. So and B is the offset, right? So W and B are the variables that we need to find, which are let's say the address of the separating hyperplane, right? So if the point is on the right hand side of this hyperplane, it belongs to class H plus, and otherwise they belong to class H minus, right? So how do we compute the margins and the separating hyperplane? So we have W is the normal of the separating hyperplane and R is the margin, right? So the distance R can be used to specify a new um, coordinate of the XA. XA here is the point that we need to test, right? So it is XA plus R, which is the margin or the distance in the direction of the normal, right? So here we normalize the normal here. W over W norm is a normalized vector and it's multiplied by R. So if you can see here, so this is the point and we add to it R in the direction of W. So we get here XA, right? So here we can find distance to the hyperplane. So the formulation here, we need to test the labeling of the point. So we multiply the label, which is +1 if you are in H plus and -1 if you are in H minus 1, meaning cats and dogs. If you multiply them by the equation of the separating hyperplane, they should be greater than R if they are in H0 and less than R if they are in H minus 1. H minus, sorry. So so this is the main equation here. So what we need to find is what? What are the unknowns? W, B, and R. So we need to find W and B such that the distance, the margin, is maximized. So the SVM is formulated as such. Maximize R such that here we satisfy all the labeling, meaning that we have all the points correctly classified in the respective classes, and of course the margin is greater than 0 and the normal vector is normalized. Okay, this is the, let's say, intuitive formulation. Another formulation that is used more in literature is this one, right? So we set the margin to 1 over W, which is related to this, right, to this equation here. So you can see that R is divided by the norm of W, which is the normal of the hyperplane, right, such that the labeling is correct. So here, as you can see, R here is replaced by 1, right? So here we need to maximize this thing, right? So we maximize 1 over X, which is equivalent to minimizing X itself. And because we have the norm, it's easier to differentiate or deal with the norm squared, right? And we multiply by 1/2 for convenience. So this is the most popular way to deal with SVM. And as you can see, this is a QP problem now. This is a QP problem because the cost function is quadratic and we have linear constraints. So you can formulate it as standard QP problem. Now we have a small example here. Let's say that we have two classes, right, +1 and -1, and we have 3 points. So x1 is in class 1, x2 is in class -2, and so is x3, right? And we need to find the optimal SVM classifier, meaning that we need to find the separating hyperplane that gives you the maximal or maximum margin between those points, right? So again, we need to formulate it as a QP problem, find the Lagrangian, find the KKT conditions, and from them we solve for W and B. So this is the problem that we have, this is the original form of the SVM that can be converted into this form, right? Right. Note that here X is transposed and we have the all ones vector. Okay, Z is the new vector that contains the unknown variables W1, W2 and the bias. So if you use Z in this form, you need to put the constraints in this form, right? Q of course is the semi-definite matrix, right? And we form the Lagrangian easily like this. We multiply by the Lagrangian variables. How many multipliers we have? 3, because we have 3 unknowns, and sorry, because we have 3 constraints that are related to the points here, right? Those points x1, x2 and x3, and here we have 3 constraints, one for each point that is classified. So those are the training points. Of course the Lagrange multipliers are greater than 0. Okay, we find the KKT conditions, stationarity, which is found by taking the derivative with respect to the unknowns and setting to 0. So we get this equation when we derive with respect to W, and this equation when we derive to respect to B. Primary feasibility, which is only the constraint, the inequality constraints, dual feasibility, and complementary slackness when we are dealing with the inequality constraints here, right? Okay. Now, assuming that x1 and x2 are active, meaning that lambda 3 is 0 in this case, right? We can solve the KKT conditions and we get those values, okay, from those equations right here, and we can check those are the optimal values.